In this lesson we're going to pick up where we left off last time and talk about inverse trig functions, and the three remaining of the 6 inverse trig functions are the ones we're going to work on in this section. The first one is the inverse cotangent function, and this inverse cotangent function looks like y equals cotangent inverse of x, and this means, just like in the last section, that cotangent of y equals x. And this occurs in specific places for where or what the domain ends up being in the range. So you want to think about what the graph originally of cotangent looks like. In our original graph of cotangent, we had a curve that was decreasing, something like this, and in particular it was trapped between two lines, and they were asymptotes, and those lines were over here and over here, and they occurred at 0 and at pi. So that would actually be the domain for the tangent graph, which means that it is the range for the the domain for the cotangent graph, which means it's the range for the inverse cotangent. So the inverse cotangent's range is from 0 to pi. And then the range over here for tangent, or for cotangent, excuse me, is actually from negative infinity to infinity, and that then would be the domain for inverse cotangent. So our domain is negative infinity to infinity, we're all reals, and our range is from 0 to pi. Secant graphs. Now, secant graph is related to cosine, and it will have similar domain and range kind of issues. We actually have the function y equals secant inverse of x, and that means that secant of y equals x, and that happens when or where the domain and the range take on certain values. So let's take a look at the graph, and I'm actually only going to draw the graph of secant on the same graph where cosine was able to have an inverse. So cosine graph actually had an inverse right here, and it occurred between the value of 0 and pi. So that's my domain, and the graph of cosine looked like this. Well, we've got an asymptote right here, and it looked like this. I'm going to draw it a little bit longer. So when we're taking a look at this, the domain is clearly 0 to pi, except on this one it has the location halfway between here at pi halves, where we have an asymptote. So that's my domain on secant, which means my range on secant would be those values. So that's 0 to pi halves, union pi halves to pi. Now, to get my domain, I have to look back at the original graph of secant and look at for its range. The range on this graph, if you'll remember, went from 0 to negative 1, and then 1 to 0. So that will be my domain for this graph. So negative infinity to negative 1, bracket 1 to infinity. And we get to equal those ones. That's why 1 and negative 1, that's why I have brackets on those, because we actually have points right here and right here on our graph that are part of our equation. Last one is inverse cosecant. Again, very similar to the rest of them. This is y equals the cosecant inverse of x, and that means that the cosecant of y equals x. And that occurs where the domain and the range have specific values. Alright, so taking a look at that, I'm going to draw the graph of a sine, because that is related to, it is a reciprocal of cosecant. And when we did the graph of sine, the portion of the graph that we actually used was this portion. And we had that then trapped between this line and this line, and those were occurring at negative pi halves to pi halves. And then the graph for cosecant looked like this and like this on those portions, and it had an asymptote through the y-axis. So the domain for this graph, the one that I've drawn, is actually from negative pi over 2 to pi over 2, and you have to leave out the x equals 0 value. So that will be the range for cosecant inverse. So my range goes from negative pi halves to 0, union 0 to pi halves. And then to get the domain, I have to look back at the range of the previous graph. So the range was just like the range for secant. It goes from negative infinity to 1, negative 1, and then union, and then 1 to infinity. And that will be my domain for inverse cosecant. We're going to do one example of this before we close up shop today, and it's going to feel very like when we did the examples in the last section. I've got inverse cosecant of negative 1, and I'm going to set that equal to theta. So the first thing I'm going to do is I'm going to rewrite this to be cosecant instead of inverse cosecant. So this is the cosecant of theta, and it equals negative 1. Now, on some of these, you're going to be able to think about the problem from there and do just fine. But in some cases, it's easier to take reciprocals to think about it. So I'm going to show you how that works on this one, not because it's absolutely crucial, but because it will be on some of our problems. So the reciprocal of cosecant is sine, and the reciprocal of negative 1 is very friendly, also negative 1. And then if you recall, the location for sine to be negative 1 between quadrants 1 and 4 is actually at the very bottom of quadrant 4 at negative pi halves. So negative pi halves is the same, or is the cosecant inverse of negative 1.